All right, folks, in this lesson, I'm going to describe or explain how to understand linear functions, okay? And we know all the qualities that I've identified, the characteristics of a function. Well, I'm going to show you how each one of these characteristics relates to a linear function, okay? So when we say linear function, what we mean is very similar to linear equation or linear expression. So let me give you an example, and what we'll do with this example is we'll go through all of the qualities and take some notes on specifics to linear functions. So let's say that the function we're dealing with is f of x equals, let's do something real simple like x minus 2, okay? So remember that this is basically the same thing as saying y equals x minus 2. So we have two variables. We have an input variable and an output variable. And so whatever we plug in for x, so like if we plugged in a 10 for x, 10 minus 2 is equal to 8, so then y is equal to 8. So when x is 10, y is equal to 8, okay? Although if I picked a different letter for x, like 17, 17 minus 2 is 15, and so when x is 17, y is 15. And so we could have an infinite number of combinations of x and y. And one way to understand that sometimes is to create what's called a T-chart, where you put your x's on one side and your y's on the other, and you put in a bunch of different ones, like, I don't know, like a lot of times people will put numbers that are in a row, like 4 and 5 and 6 and 7. Well, 4 minus 2 is 2, so when x is 4, y is 2. When x is 5, 5 minus 2 is 3. 6, when x is 6, 6 minus 2 is 4. Now, notice something interesting here. 7 minus 2 is 5. That in this particular case, our x's are going up by 1s, but our y's are also going up by 1s. 2, 3, 4, 5. Now, that won't always happen. That is specific to this particular function and functions that are like it, okay? How much y goes up by is actually related to number 5 here, the rate of change. We'll talk about that in just a little bit, okay? All right, so we're going to go with this function f of x is equal to x minus 2. And so let's go through our 9 characteristics, okay? I'm going to do it with a different color here so that so we said that the way we find the f of 0 is we plug 0 in for x. So f of 0 is going to be equal to whatever 0 minus 2 is. Well, 0 minus 2 is negative 2, and so f of 0 is negative 2. And so for this linear function, f of 0 is negative 2. Now we're going to identify the roots, or the zeros. Now you can make a note on this in terms of roots for a linear function. So let's make a note here. For a linear function, there will always be exactly one root, or 1 0, okay? There's only ever 1 0, and there is always 1 0 for a linear function, okay? Now there is a certain kind of linear function that we're going to talk about in a little bit called a constant function. With a constant function, there's typically not a 0, okay, but we'll get to that later. But for linear functions, there will always be exactly one root. So we don't have to look for 2 different answers or 5 different answers, okay? We know that there's only going to be one answer. And we said the way that we find the root is we take our function, whatever it is, and we set it equal to 0. So we put in the place of f of x, we put the number 0. We put 0 is equal to x minus 2. Now it's a linear equation, and we just solve the linear equation. Add 2 to both sides, and we wind up with 2 is equal to x, or we could say x is equal to 2, okay? So the roots of this particular linear function, or the root, the 0, is x equals 2, okay? And so that is our root, all right? So make sure you make a note of this. Now let's move on to the sign chart. What we said with the sign chart is to make a sign chart, we're going to draw a horizontal line, then we're going to put infinity on the right side, we're going to put negative infinity on the left side, and then we're going to mark all of the roots in the middle of the line, okay, or somewhere in the middle of the line, and we're going to put them in order from smallest to largest. Well, linear functions only have one root, and so we're just going to put that one root right there in the middle, which is 2. And so this is, we're almost done. And then remember what we said we had to do? We had to take numbers on each of the segments. So we have a segment that runs from -infinity up to 2. So we're going to pick any number that is on this segment, okay? So it has to be all the numbers less than 2. But do not pick 2. If you plug 2 in, you'll get 0, okay? So we're going to pick something less than 2, like, I don't know, -3. So if we plug in -3 here, identify f of -3, plug in -3 for x, -2. Well, -3 minus 2 is -5. That's a negative. It's a sign chart. The sign of that answer is negative, and so we are going to put a negative symbol above the line. Okay? What that means is that every output value is negative for less than 2. So anything you plug in that's less than 2 into this function, the answer will always be negative. If you put in a 1, 1 minus 2 is -1. Put in 0, 0 minus 2 is -2. If you put in -13, -13 minus 2 is -15. Okay? Now we're going to find the sign that goes on this side of the segment. And so we're going to put in a number larger than 2. Okay? So let's put in, I don't know, let's say 5. So f of 5 is equal to 5 minus 2. Well, 5 minus 2 is equal to 3. So f of 5 is +3, and because it's a +3, we're going to put a plus right here. All right, so now let me make a comment about sign charts for linear functions. For linear functions, okay, because there is only one root, there will always be exactly 2 segments. There will be 2 segments on the sign chart. One of the segments will be negative, and the other will be positive. Positive. There we go. Okay. So you see here, we have negative here, we have positive here. The other possibility is if this one is positive, then this is going to be negative. Okay. That will always be the truth on sign charts for linear functions. Okay. All right. Great. Now we're going to move on to the constant term. Okay. Well, we said that the constant term, all we do is we just look at the function itself and look at the term that doesn't have an x with it. Well, this -2, that doesn't have an x with it, therefore the constant term is -2. Now, I do want to point something out here. Do you notice that the constant term is the same as f of 0? F of 0 is -2, and the constant term is -2. That will always be the case with linear functions. The constant term will always be the same as f of 0. Okay? So you'll always have the exact same answer under number 1 and number 4 when it's a linear function. You're actually going to find that it's going to be we're going to see that exact same thing again with quadratic functions. We're going to see that exact same thing again with polynomial functions. Okay? All right. So now, number 5 is probably the most important feature of linear functions. Okay, so we're going to talk a little bit about the rate of change. So the rate of change in a linear function is very special. The rate of change, rate of change, let me not put that there. For linear functions only, is represented by the letter m. Change is m equals. Okay, it's a formula. It's m. Now you've seen this before. It's called the slope. You've probably seen that before. Okay, that's what the rate of change is. It is the slope, okay? And it has a formula. Here's how we're going to find the rate of change, which is m. What we're going to do is we're going to do a fraction, and what we're going to do is we're going to take two x values and we're going to plug them in to the function and get two output values, okay? We're going to call those two input values, or we're going to call the input value A, and we're going to call the output value B, okay? And so what we're going to do is we're going to select two x values, A and B, okay, where A is typically the smaller of the two values and B is typically the larger of the two values. So let's say you select the two numbers you select are 5 and 11. A would be your 5, 11 would be your B, okay? And so what we do is this. It's a formula. In the denominator, we just have B minus A. In the numerator, we have f of b. That means plug b into the function and get an output. So we have output minus and then f of a. So we have two outputs, the output when b is plugged in and the output when a is plugged in. And we do the output when b is plugged in minus the output when a is plugged in. That's the numerator, and the denominator is b minus a, okay? Sometimes you may have seen this as y2 minus y1 over x2 minus x1. This is the exact same thing. Look, x2 is your larger x value, y1, or x1 is your smaller x value, y2 is the y value that you get when you plug in the x2, and y1 is the y value you get when you plug in x1. Okay, so these two formulas are exactly the same, okay? So select two x values and plug them in to get two f of x equals y values called f of a and f of b, okay? All right. And once you have those numbers, now what you're going to do is you're going to solve the formula to get your m. So we just have to. So we said previously, let's let a equal 5 and let's let b equal 11. Okay. So what we're going to have here is our formula over here for the rate of change is we'll have m is equal to, well, we know it's going to be 11 minus 5 on the bottom. On the top, it's going to be f of 11 minus f of 5, okay? And so we have to find out what is f of 11 and what is f of 5. Well, we find that by plugging in. We put an 11 in for x in the f of x. So we put an 11 here. F of 11 is equal to 11 minus 2, okay? So it's going to be 11 minus 2. Well, 11 minus 2, that's 9. And so what we're going to have here is f of 11 is 9. Now plug in 5, so it'll be 5 minus 2. So 5 minus 2, well, 5 minus 2, that's 3. So 9 minus 3 over 11 minus 5, okay? And here's what we have. 9 minus 3 is 6. 11 minus 5 is also 6. And 6 divided by 6 is equal to 1. And so in this particular function, in this particular linear function, the rate of change is 1. Positive 1. So we would say m equals 1, okay? Now, what we're going to eventually get to, what I want you to notice is this, is that the rate of change, another way of understanding the rate of change is it's the coefficient of the x. Whatever is in front of this x. Now, you don't see a 1 there, but the 1 is implied. So the last point I want you to write down is, for a linear function, the rate of change is simply the coefficient of the x term. The rate of change is simply the coefficient of the x term. Okay? And so this function right here, we have f of x is equal to, so the rate of change, which we call m, is equal to m times x, well, let's not put it in parentheses, m times x, okay? And then we have the constant term, right? And the constant term for a linear is often called b, usually called b. Okay, although we just selected B for A and B, so don't get that mixed up. Oops, usually called B. And so what we usually wind up with is the function itself is equal to m, the rate of change, times the x variable plus whatever the constant is, which we often call b. You've probably seen this before. You actually probably learned it as y equals mx plus b, but note that we're saying that f of x and y are the same thing. So we can say y equals mx plus b or f of x equals mx plus b, okay? And so this is what we wind up with. Another way of saying it is f of x is equal to, since m is the rate of change, we can actually say rate of change x plus constant. Okay, and so oftentimes these answers here on these 4 and 5, you don't even have to do the calculation. You know, so if I said f of x is equal to negative 4x plus 7, well, that means the rate of change is negative 4. So over here under rate of change, you can just say m is equal to negative 4. The constant is 7. You can just put that right here. Number 4, constant term is 7. And since we already said that the constant term is always equal to f of 0, you can put a 7 up here. So you can see that of these 9, 3 of them can actually be answered really quick just based on what the linear function looks like, okay? Rate of change is negative 4, constant term is 7, f of 0 is 7. Now we only have 6 left to answer. All right, so now let's look at number 6, intervals of increase, decrease, and constant, okay? This one's actually pretty easy because linear functions only have one of them, okay? So linear functions have only one, have only an interval, interval, have only, let's see here, let's say it this way, interval of increase or, not and, or an interval of decrease, okay? Now, linear functions actually don't have a constant, okay? Unless it is what we call a constant function. I consider a constant function, even though it's linear, I consider constant functions to be different than linear functions. So we'll get to that when we get to constant functions, okay? So with a linear function, there's only going to be an interval of increase or an interval of decrease. And the interval is always the same. Oops, I'm really messing up with spelling today. Always. It is always negative infinity to positive infinity. Because linear functions are only ever increasing over their entire domain, or they are always decreasing over their entire domain. Okay? Those are very special functions. I won't get into it now, but it's a very special kind of function that is always increasing over its entire domain or always decreasing over its entire domain. And it's based on whether the rate of change is positive or negative, okay? So an interval of increase is going to be if the rate of change, well, let's say m. The rate of change is m, okay? If m is a positive number, and it's an interval of decrease if m is a negative number, okay? And we can see here that m, in this case, m is positive. Okay, you can see the rate of change, the coefficient of x is a positive 1. Therefore, this linear function only has an interval of increase, so we're going to say increases for, and we're going to put negative infinity, positive infinity, okay? And that's all we're going to say for intervals of increase, decrease, and constant. Linear functions only have one of these two, so we're going to pick one of them, and it's going to be based on the sign of the rate of change, and then we're going to say negative infinity to positive infinity, okay? All right, now let's talk about the domain. Well, the domain of linear functions, so we're asking what are all the numbers that we can plug in to this linear function and get a defined answer, okay? Well, in this case, really, look, there's nothing in here that indicates that there's any number we can't plug in. We can take any number in all of the real numbers and subtract 2 from it, okay? And that's actually the same for all linear functions. So here's what I'm saying to you. For linear functions, the domain is actually all numbers. Oftentimes we'll say all real numbers, and so the way we write all real numbers is we do a double vertical bar. We make an R, but it has 2 lines instead of 1. We say all real numbers, but I told you the way we're writing domains is as an interval. And so we're just going to write it as negative infinity to positive infinity, because every single number from negative infinity to positive infinity can be plugged in to any linear function and evaluated, okay? All right, so that was a long way of basically saying if it's a linear function and you're going to write the domain, you're just going to write negative infinity, positive infinity. It's all of the numbers, okay? So now, let's look at question number 8 here. It's asking for the limits of the function as x approaches negative infinity and the limit of the function. I'm not going to explain limits to you right now. I'm just telling you this is how you write it. The limit of the function as x approaches positive infinity. All right, what we said is this. If we plug in really small numbers, now when I say small, I mean they're big numbers with a negative sign in front of them, okay? So for example, negative 1,000 is smaller than negative 100. This is smaller than negative 100, okay? Even though it looks like a larger number, if we get rid of the negatives, it looks like a larger number. But because it has a negative in front of it, it's a smaller number. So here's what we're basically imagining. We're imagining that we're plugging in like negative, 1 million. Let's just do that. Let's first think of it as we're plugging in negative 1 million, okay? Well, if I put negative 1 million in here, what do I get as an answer? Well, negative 1 million minus 2 is negative 1 million and 2, right? Negative 1 million and 2. Well, what if I put in negative 5 million? Well, then we'd have negative 5 million and 2. And here's the funny thing. With linear functions, when you're plugging in numbers, if the x is a big number in one direction, then the y is also going to be a big number in one direction, okay? In this particular case, we're putting in a very large magnitude negative number, and we get a very large negative number. So when we put in a negative, we get a negative, okay? And so what that means is that the limit of f of x in this linear is actually negative infinity, okay? And here's the idea. With linear functions, your answers to these two questions will only be, only either negative infinity or positive infinity. And here's a really easy way to do this for linear functions, because I want to give you an easy way to answer the question, okay? Put in negative 1 million. If your answer is negative, okay, then the answer here is negative infinity. If you put in a big positive number and you get a positive number, so if I put 1 million in, 1 million minus 2 is 999,998. But that's still a positive number, and so the answer is positive infinity. So as the inputs become more negative, the outputs also become more negative. And here, as the inputs become larger and larger positive, the outputs become larger and larger positive. Okay? So, negative inputs become negative inputs. Positive inputs become positive inputs. And so over here, we're going to say the limit of f of x as x approaches negative infinity is negative infinity. The limit of f of x as x approaches infinity is infinity. Okay? Now you may say, well, Mr. Ryan, when is the answer going to be reversed? Under what circumstances would I make the answer to the negative infinity? Under what circumstances would this be positive infinity? Well, I'm glad you asked. Let's say that we have f of x is equal to negative 2x minus 7, okay? Now here's what's going to happen. If I put negative 1,000,000 in for x, and I multiply negative 1,000,000 times negative 2, well, what's negative 2 times negative 1,000,000? Well, a negative times a negative is a positive. So negative 2 times negative 1,000,000 is positive 2,000,000. And then we're going to subtract 7 from that. Sorry, you probably can't see this over here. Let me redo this. All right. Negative 2 times negative 1,000,000 equals negative 2,000,000. Or not negative, it's positive, sorry. Negative times a negative is a positive. So now, when x goes towards the negative, the outputs actually go towards the positive, okay? And the reason for that is this. It's because the rate of change is a negative number, okay? And so here's what we're going to say. When the rate of change is positive, then the answer to these two is going to be the same as what you see here. But when the rate of change is a negative number, like negative 2 is over there, it reverses it. And see here, what we would do here, if I plugged in 1,000,000, 1,000,000 times negative 2 is negative 2,000,000. So my positive numbers are becoming negative. So this, all of this is based on m, the rate of change. It's based on the rate of change. When the rate of change is positive, a positive number, the answer here is going to be the same as what you see here. The answer here is going to be the same as what you see here. But when the rate of change is negative, like negative 2, then whatever you see here, you're going to do the opposite up here. Okay? All right, we have one more thing to cover. And then we will maybe try a couple more examples. We're going to do the range. Well, the range for linear functions, because here's the thing. If for range, if if 8 has negative infinity as one answer, and positive infinity as the other answer, then range is the interval is negative infinity to positive infinity, just like the domain. And that's the case with all linear functions. All linear functions have a range that is negative infinity to positive infinity, because for number 8, one of these will always be negative infinity and the other one will always be positive infinity. And that's why the range, well, that's not the best explanation why, but that's basically why the range will always wind up will always be negative infinity to positive infinity. And here's what that means. Basically what I'm saying here with linear functions. Let me be a little more mathematical. With linear functions, you will always be able to plug in any number for x, and every value will always be a possible answer for y. So for x's, every single number will be included, and for the output, for y or for f of x, every single value will be an answer. So you can select any number, any real number, put it in for f of x here, not for x, for f of x. replace f of x completely with any number, like negative 3,497,667,843. That's just any number equals x minus 2, and you can solve for x. Every single number in the real numbers, and like I said, this is how we write all real numbers, is an answer for all linear functions, okay? All right, let's try some examples now. We'll do maybe 2 or 3 different linear functions, and we'll run real fast through all 9 of these. You'll see how fast they go. All right, let's try an example here. Let's say that we have f of x is equal to negative 4x minus 7, okay? And this is a linear function because we have x to the first power here, okay? And it says f of x is equal to, so we have 2 variables. We have a y and an x, okay? So it's a function, right? Now remember what we said? We said that real quick we can do number 1, number 4, and number 5, okay? What's the rate of change? The rate of change is the coefficient of the x, that's negative 4. So m is equal to negative 4, okay? What's the constant term? Well, the constant term is the part that doesn't have an x. That's negative 7. And we also said that the f of 0 is always going to be the same as the constant term for linear functions. So that's also negative 7. And just to verify, let's go ahead and put a 0 in for x. Negative 4 times 0 is 0. Minus 7 is negative 7. So we're good to go. All right, now let's identify the zeros. Now we said that there's only one root in a linear function. And so what we do is we set the function negative 4x minus 7, we're going to set it equal to 0. That's how we find the root, okay? So we're going to add 7 to both sides, cancel, and we get negative 4x equals 7. Then we're going to divide by negative 4, okay? Now we have x is equal to, now it looks like 7 over negative 4, but I want to remind you that we don't put negatives in denominators. If there's a negative in the denominator, we either move it to the numerator or we put it in front. Let's just put it in front. So we'll say negative 7 over 4. So the only root, the root of this linear function is negative 7 over 4. Okay? So we're going to say the root is x equals negative 7 over 4. Now we can make the sign chart. Remember, to make the sign chart, we just simply draw, I'm going to do it kind of over here. We just draw a horizontal line. We put infinity on the right side. We put negative infinity on the left side. We draw a vertical hash mark somewhere in the middle, and that's where we put the 0, the root. So we're just going to put here negative 7 over 4. Okay? And then what we want to do is we need to plug in numbers that are smaller than negative 7 over 4 to see what the sign is over on the left side. Well, you may say, well, I don't know what's less than negative 7 over 4. Well, just to be safe, you could pick something like negative 10 or negative 100, okay? Let's do negative 10, okay? So we're going to put negative 10 in for x, so we get negative 4 times negative 10 minus 7. Well, negative 4 times negative 10, that's 40. And 40 minus 7, well, that equals 33, which is a positive number, and therefore we can put a plus over here. Now we need a number larger than negative 7 over 4, and let's say, how about 1? Any positive number is larger than negative 7 over 4, so we can do negative 4 times 1 minus 7. Well, negative 4 times 1 is negative 4, minus 7. Negative 4 minus 7 is negative 11. It's a negative number. Therefore, on this segment, we're going to put a negative. And that's consistent with what we said. We said that linear functions will always have one of them positive and one of them negative. Okay? And so you can sort of shortcut that. Once you know that one of them's positive, you can just make the other one negative. Now, that's only if it's a linear. That's only if it's a linear function. Okay? All right, let's go down here to intervals of increase and decrease. And we said that linear functions only have one of them, okay? Well, what's this one going to be? This one's going to be an interval. Well, we said that it's based on the rate of change. We said if the rate of change is positive, it's an interval of increase. But if the rate of change is negative, it's an interval of decrease. Well, we have a negative rate of change, therefore we have an interval of decrease. Interval of decrease. And we said that it will always be negative infinity up to positive infinity. So we're done. Domain, well, we said all linear functions have a domain of negative infinity to positive infinity. We are allowed to plug in any number into any linear function, okay, including this one. Now we have the limit, this is what we call the end behavior. The limit of f of x, meaning what are the outputs of f of x as the x values become more and more negative, okay? And so we did have a trick on this. We said that basically if the rate of change is positive, then the answer to this is going to be the same as this, okay? But look, our rate of change is negative, and so we have to do the opposite of what we have here. Well, this says x approaches negative infinity, and since the rate of change is negative, we're going to put positive infinity. And then down here, the limit of f of x as x approaches positive infinity, and since the rate of change is negative, we're going to put here negative infinity. Now watch this. There's actually another way of understanding this based on the sign chart. Look, when x is negative infinity, look over here. When x is approaching negative infinity, right, we have all the positive numbers. That's why we put positive infinity. And here, the limit of f of x as x approaches positive infinity. So if we go over here to positive infinity, you can see on this side, on this segment, we have all the negative numbers, and therefore the answer is negative infinity. So you can actually use the sign chart also to understand the end behavior of a linear function, okay? You're actually going to find that that's true even with other kinds of polynomial functions as well. All right, now, the range, last part. Well, we already said that with linear functions, you can get any number as an output. Every single number qualifies as an output value in linear functions, and therefore the range is always going to be negative infinity to positive infinity for a linear function, okay? All right, let's do maybe one more example. Do one more example, and then... All right, let's say that f of x is equal to f of x equals, let's do like 2/3 x plus 9, okay? 2/3 x plus 9. I actually don't like this marker. I'm going to get rid of that. Use this one. 2/3 x plus 9. Okay, well, the rate of change is 2/3. So here, rate of change, we're going to say m is equal to 2/3. The constant is positive 9. So constant term is 9, and that means that f of 0 is also equal to 9. To find the roots, or the root, there's only one, we're going to take our 2/3 x plus 9 and set it equal to 0. Okay, so we're going to subtract 9 from both sides. We're going to get 2/3 x equals negative 9. To cancel the 2/3, what we're going to do is we're going to get rid of the denominator first. So we're going to multiply by 3. So over here, we're also going to multiply by 3. Cancel. We get 2x is equal to negative 9 times 3 is negative 27. Divide by 2, divide by 2. And here's what we end up with is x is equal to negative 27 over 2. That is our root of this linear function. So x is equal to negative 27 over 2. Now that's, if you could convert this into a decimal, it would be the same thing as negative 13.5. Now that's helpful when you're about to do the sign chart, okay? So let's go ahead and do the sign chart. All right. We know that we need the root, negative 27 over 2, for the sign chart. I'm going to go over this way a little bit because it's cramped over there. We're going to put positive infinity here, negative infinity here. We're going to draw our hash mark. We're going to put in negative 27 over 2, which is the same thing as about negative 13. So if we're going to plug in something smaller than negative 13, we've got to pick something less than that. So how about maybe negative 20, okay? So let's put negative 20 in here. Actually, I want something divisible by 3. How about negative 21? Let's do negative 21, okay? All right, so we're going to put in 2/3 times negative 21 plus 9. So negative 21 times 2 is negative 42 over 3 plus 9. Negative 42 divided by 3, you can actually divide 3 into 42. It's 14. So we got negative 14 plus 9. Negative 14 plus 9 is equal to negative 5, and so we have a negative value on the left. Because we have negative values on the left, we must have positive values on the right. And so we're done with the sign chart. Let's go down here to intervals of increase, decrease, and constant. Well, the rate of change is a positive number, so that means we have an interval of increase. And that the interval of increase is negative infinity to positive infinity. Because all of the intervals, we only have one of them, and it's always negative infinity to positive infinity for linear functions. The domain, we already know that the domain is negative infinity to positive infinity. By the way, we already know the range is negative infinity to positive infinity because we can get any number as an answer. Every number is an answer for every linear function. Lastly, we've got the end behavior, okay? Well, as x approaches negative infinity, well, here's our negative infinity. Look at this. What's next to our negative infinity on our sign chart? Negative. And that means that the answer to this one is going to be negative infinity. Now let's, as x approaches positive infinity. Well, what's next to our positive infinity on the sign chart? Positive. And that means the answer is positive infinity. And there we have identified all of our important characteristics of a linear function, okay? So now what we're going to do is we're just going to do a couple of sort of different kinds of problems where instead of being given the function, you're actually given information over here, in which case you then have to get the function and answer some of these questions.